Hi, I'm Rika Kovács. I'm a PhD student at Eötvös Loránd University in Hungary, and I'm working on finding memory bugs in C++ code. And the way I do it is by enhancing and using static analysis tools for this purpose. Initially, I planned for this talk to focus on my most recent, more specific results, but in the end, it turned out to be a bit more general than that. But I hope you'll enjoy it anyway. And a quick word about the research group at our university that I'm a part of. We call ourselves the Code Checker Lab, not only because we literally check code, but also because Code Checker is the name of an open source tool that we developed together with our colleagues at Ericsson Hungary. And you can see a screenshot on the right-hand side of the slide. It's basically a viewer extension to all the static analysis tools that we are using. And it is particularly suited for teams and companies to use because it's really good at aggregating a lot of analysis results, and it makes it convenient to browse and compare them. But actually, I am working on the other side of this slide. So the other part of the group works on actually improving the logic of these static analyzers. And we've decided not to create our own little tool, but instead contribute to large open source projects, more specifically the LLVM compiler infrastructure project, which has some great static analyzers for C and C++ in Clang Tidy and the Clang Static Analyzer. And in this talk, I'd like to focus on the Clang Static Analyzer because that's what I've been mainly working on in the past few years. And the main motivation for this talk is the memory safety issue of C++. You would think that the language has been around for such a long time that this clearly must have been fixed already, right? Well, wrong. As shown by this slide that I borrowed from Matt Miller, who's from the Microsoft Security Response Center. And this picture clearly shows how even in the recent years, around 70% of all the critical vulnerabilities that are being fixed by Microsoft, these still come from C++ memory safety issues. And similarly, over at the Chromium project, they found that around 70% of their high impact security bugs come from memory safety issues. So I think these statistics show that something clearly needs to be done about it. And so the question naturally arises, like, will using modern C++ save you all this trouble? And the answer is yes and no. There are a lot of new C++ language features or ideas or idioms that have mitigated some of the risks of the past. For example, it is no longer customary to just have random new and delete statements lying around in your code. Of course, manually calling these operations is really error prone because it's easy to forget to call delete or to call it twice or all kinds of similar problems. So now we usually use the RAII idiom, which is terribly named, but it's actually just wrapping all the row pointers that point to dynamically allocated memory inside a C++ object, because the C++ object will now have a constructor and a destructor that are automatically called by the compiler. So if the author of the type allocates memory in the constructor and deallocates it in the destructor, then all the memory management will basically happen automatically behind the scenes. So you just have to write it correctly once and then you can use it without worrying about calling deletes and stuff like that. So using this idiom has certainly mitigated a lot of the problems that existed before. But as we will see, creating use after free situations is very much possible in modern C++ as well. And we'll see that on this small example that was reported by Google engineers who said that they have seen a great number of these types of bugs in their enormous code base, even though it's using modern C++ features all over the place. So first we have a standard string, that's straightforward. And then we create a string view. Now a string view is basically a glorified pointer. It's either a pointer and a length or two pointers wrapped up in a C++ object. And it's all about handling strings efficiently. So the big difference between the string and a string view is that the string actually owns the memory underlying the character sequence that it holds. And the string view doesn't, it just peeks into someone else's character sequence. So it's great to use when you want to avoid copying large strings, but you have to be careful to only use the view as long as the underlying, the referenced string is also alive. And that's exactly the problem in this example as well, because the concatenation operation on the right-hand side yields a temporary string, which will be destroyed at the end of the full expression, which means the end of line 7. So the string view is going to point to deallocated memory after line 7. And so I myself am curious, how are C++ language designers sleeping with all these fancy errors they have? And I guess not that well, because, for example, Herb Sutter, who is the chairman of the C++ Standards Committee, has been working tirelessly for years to think of new ideas to help mitigate these issues in a systematic way. So one of his recent ideas was to introduce a lifetime analysis into the C++ compilers. So the rough idea behind this lifetime analysis is that the compiler would categorize types into owner and pointer kind of types. So these are like generalized concepts. And the compiler would also try to track the set of locations that a pointer could point to. And whenever some kind of deallocation happens or the location goes out of scope, then the entries in the points to sets will be invalidated. And whenever a pointer is used that can possibly point to an invalid location, then the compiler will give a warning. Now, the greatest barrier to this analysis to be really useful in practice is that it has quite strict requirements towards the project that is being analyzed. And even though these rules are all great recommendations for any C++ project, most real-world code bases don't really conform to these rules. So in real life, projects would experience a lot of false positive warnings from this analysis. Now, in the latest update, the team has shifted their focus from supporting the general case, which seems problematic in reality, to dealing with simple but very common cases that don't have any special requirements towards the code base. And these statement local cases have been very successful. So they have been implemented in both Microsoft's Visual Studio IDE and the Clang compiler itself. And I would just love to highlight that one of the Clang implementers was my dear friend Gabor, who added this analysis to Clang together with our friend Matthias from Germany, which is cool. And I'd like to show you a quick example of what the compiler warnings can now catch. So it's very similar to the one we've seen before. There is some string concatenation going on. So the result of that is a string object, which the author clearly knows because then it calls the cstr method on the string. So this method will return a row pointer that points to the underlying buffer of the string object. So it's very similar to a string view, just the old version of it. And we're going to have the same problem at the end of this line, that the string was actually a temporary object, and it's going to be destroyed at the end of the full expression, at the end of the line. So our const char, a pointer, is going to point to the allocated memory. So the compilers can now catch this, which is great. But let's tweak the example just a little bit. So in the previous version, all the events in the code that led to the bug were very close to each other. They all basically happened on the same line. Now let's say that in the second example, these events will be more dispersed in the code. And the other big difference to the previous example is that the string is not going to be temporary anymore, because temporaries only live inside one expression, so that wouldn't work for this longer example. But the idea is the same. In this case, the string is local to this function. So instead of being destroyed at the end of the expression like before, it is going to be destroyed at the end of the function. So if we try to return the buffer pointer of this string from the function, then the caller will receive a pointer to invalid memory, because right when the function exits, the string is going to be destroyed. And so the second example is out of the scope of the statement local lifetime analysis that's in our compilers today. So we'll need a more powerful tool for that. The static analysis tools should be the next thing you should reach to when your compiler fails you. I mean, it's understandable that compilers can't do as expensive analysis as external tools because they have to stay fast for compilation. So that's when something like the Clang static analyzer comes in handy. And I've already introduced it a little bit in the beginning. It's open source. It's built into the Clang compiler. And it's also built into a lot of IDEs now, like Xcode or VS Code, and so on. And one of the greatest things about it is that it produces path-sensitive bug reports, which means that the events leading to the bug can be visualized very nicely, and the analyzer will insert explaining notes at all the important points along the bug path, so it's really easy and convenient to understand the bug. So the Clang analyzer can perform analysis on different levels. Because it's built into the Clang compiler, it has certain data structures readily available to it. And one of them is the abstract syntax tree, of course. So pattern matching on the AST is mainly suitable to find suspicious code patterns or code smells. But it's best if you keep it simple and local. So a primitive example would be a division by a literal zero. But once you need to track variable assignments, then it starts going out of the scope of syntax-based analysis. Luckily, the analyzer can also do flow-sensitive analysis because it also has access to the control flow graph of each function. Flow-sensitive analysis is great for checking if a certain property is true on all execution paths in the code. But unfortunately, it doesn't really have the machinery to recognize that a certain execution path is actually never going to be executed in real life. So for example, the path I colored red on this little toy CFG. So we know that that line is infeasible because two contradicting path conditions would need to be true at the same time. But the flow-sensitive analysis will not really recognize that. Because to keep the algorithm small and simple, branches are always merged at the end of the branching statements. So at the merge points, the analysis will lose the information that it had on the individual branches. So if we want to do better than that, we need to bring out the big guns. Path-sensitive analysis is the big specialty of Clang Static Analyzer. And it has its own data structure that it builds during the analysis to record all the information it needs. And it's called the exploded graph. And now, if you guess that it's basically an exploded version of the control flow graph, then you are not very wrong. To see a super quick example on how it works, let's consider the little code snippet on the left-hand side. And let's assume that the value of x is unknown. So it's some kind of input to our program. It may be that this snippet is inside a function that has x as a parameter or something like that. So we have two options at the first if statement. We either assume that x is going to be 0, in which case we proceed to execute the next line and then go to the second if statement. Or on the other hand, we assume that the x is going to be not null, in which case we jump to the if statement right at once. And now we can already see the greatest difference between the exploded graph and the CFG is that these two branches are not going to be merged together. Instead, the analysis will proceed on both branches, taking note of the constraint on the unknown variable that we needed to get to that path. If we want to express this more formally, then we will call the collection of constraints on unknown variables that need to be true for us to be on the path on which we are, the path condition. And so whenever the execution forks, we are going to add a new constraint to our path condition. And so the path condition will uniquely identify the path that we are on at the moment. So we can continue the simulation and expand the path conditions on all of the new branches as well. But then if we look closely, we will notice that that two of the path constraints have contradicting conditions in them, which means that they can never be true at the same time. So those paths are actually infeasible. And the Clang Static Analyzer has a component called the constraint manager that gets called in all of these situations to check if the constraints are indeed feasible or not. And if it can prove infeasibility, then it will instruct the analyzer to stop exploring those paths. And it's not only important to save compute power, but also because it affects the precision of the analysis. So if we would continue the analysis on those paths and would accidentally find bugs on some of them, then those bugs will be presented to the user, and the user will be very annoyed when they find out that those parts of the code will actually never execute in real life. Now, if you're thinking to yourself that path pruning is great, but this is still an exponential algorithm, then you would be right. And we need to make some compromises here for the analysis to be practical on large industrial projects. And the way the analyzer handles this problem is that it keeps a budget of various parameters of the analysis. So it has a limit on the number of nodes to analyze, the recursion depth, loop depth, all those statistics. And it's going to cut off the path where those limits are reached. Now, I mentioned all these data structures that make the analysis possible, but I didn't really stress how far they reach. It's actually because the exploded graph is essentially generated from the control flow graph. They have the same scope, so in theory, one exploded graph is generated for one function in the code. So one might wonder, can the analyzer do interprocedural analysis then? And the answer is yes, it can, of course. So the default mechanism it uses for interprocedural analysis is inlining, which is very similar to what a compiler does. What's important is that method is context sensitive. So if a particular function is called at different places in the code, it's going to be evaluated each time separately in the given context that it appears. So it might happen that completely different code paths will be exercised in the same function into different call sites. There are some requirements for inlining to be able to happen. So the body of the function needs to be available, and we need to have remaining reserves in the analysis budget, but otherwise this is the default mechanism. Another possibility is that a checker would evaluate a given function call. So checkers are these independent little modules in the analyzer that anyone can write, and they contain the specifics of a given bug type. So they specify the conditions that need to be fulfilled for a given bug to be present in the code. And I have the opportunity to say to the engine that if it sees this particular function call, then the checker wants to have control because it knows better how to evaluate that call. And then if all fails, then the analyzer will fall back to something called conservative evaluation, which is actually doing nothing, plus a bit more, because whatever the function call could touch needs to be invalidated so that the analysis data remains correct. So there's some information loss involved, but at least it remains correct. Now that we've discussed the general properties of the analyzer, we can move on to the specifics. So it has had checkers to catch memory-related errors for a long time, but they actually work best on old type of C++ code. And to see why, let's move to the next slide. So the problem with modern C++ code from the viewpoint of static analysis is that library files became increasingly complicated, and the analyzer cannot really deal with that code just with its default machinery. So the main point is that the analyzer cannot analyze what it cannot see. It needs to actually process all the statements that lead to some kind of bug. So you can see that if I cause a division by zero error using my little primitive vector implementation, then the engine is able to catch it because it is able to inline and process all the methods that I use. While if I do the same using the standard template libraries vector class, then I don't get a warning because the vector's methods were actually not processed and explored. Now, if you remember the slide about the interprocedural analysis, then you can remember that we have one more option left if inlining can't do the job, which is to delegate the modeling of the methods to checkers. And that's what I've been doing for quite some time now. First, let's recap a string related situation that we already know by heart. I just made one slight modification to make the corruption of the string more explicit in the code. So first we have a string that allocates some kind of buffer. Then we obtain a row pointer that points to this inner buffer. Then, however, something happens to the string that invalidates all pointers pointing to the buffer. So these conditions are actually specified in the C++ standard, and calling the clear member function is one of them. Well, the standard actually doesn't specify exactly what happens to the string with these operations. It leaves a lot to the compiler, to the specific implementation. But it may very well happen that a new buffer will be allocated for the string, and the correct buffer pointer now point to this new place. However, our pointer still points to the old place, so that's a problem. Now, what is the sequence of events we need to be looking for if we want to report this kind of bug? Well, first, we need to find a place where the row pointer is obtained that points to the string buffer. This will help us record an association between the pointer and the string. Then we need to watch out for any kind of operation on the string that modifies the underlying buffer. And finally, we need to find any uses of the row pointer that is now invalid. And this checker was quite a success in that it found errors in quite popular open source C++ projects. And another notable fact is that all projects have fixed these bugs within 1 day of reporting. So that part was great. In a more recent work, we have a similar situation to the previous one, just using string view instead of a row pointer. Now this was tricky because it looks identical to the previous case, but because string view is a C++ object and it's fairly complicated, it's actually quite laborious to support it in this case. So the events we are looking for in the code are exactly the same as the previous case. They are just harder to implement. So first we need to find a place where the string view starts to reference the string. This one is a bit difficult due to all the magic that is involved in C++ object construction in the compiler. But if we have it, then recognizing string modifying operation is the same. And finally, we need to look out for all the possible situations where the invalidated view may be used. So even though the implementation for this project is mostly done, there are some very important tasks remaining. For example, one thing that I was really hoping to bring you for this workshop was a comparative analysis of different string view implementations from a static analysis point of view. But it turned out to be one of those projects that you think you'll do real quick, and then it turns out to be a monster that you need to slay first. So that's still in progress. And then probably the most exciting step is to evaluate the checker on big open source C++ projects. And then upstreaming to the official Clang repo so that everyone can benefit from the change. Now, I'd like to thank you for your attention. I hope that there were bits in there that you found interesting. And if you'd like to learn more, please follow the links on the slides or ask me in the Q&A section. Thanks again.